some of my work and to put it in a larger context. So it's not only my own work, but a little bit what I did, my experience around this topic, because I thought I should not be too specialized. I should be a little bit more general. So yeah, so before I was at this international university, international university where I met Anka, and then we was renamed. It's a private university, so at the end of when there's no financing, you're a little bit bankrupt. You're looking for another sponsor. The Czechos family sponsored it. Now they pulled back, and now it's called Constructor University. So you see, it's a former military campus, nicely green, a little bit like here the weather. So you see also they have it's also a little bit grayish. So on the right side is a building. This is on the Daisy campus. It's a little bit outside of the city. And the city of Hamburg want to have a city of science with a new building, new enhanced university. So this is a nanoscience building. It's part of the physics department. And on the right side, you don't see it. It's not yet. They don't start. The chemistry will also move out from the city, go there, and it will be altogether. There are many international institutions, so it's a lively area. So good. Yeah. So I decided to talk a little bit about transport of small molecules across membrane. So, what for? I think so. Okay. Benjamin would say this is obvious because all the cells, there's an inside, there's an outside, but there's a wall, and then you have transport across it because otherwise there's not a real life. And I will not talk about everything. I cannot explain only maybe a few things. So. But you likely to have heard it in the press. We have this problem with antibiotic, lack of antibiotics, multiple drug resistance, and yeah. And I will put this a little bit into context. So yeah, okay, yeah, good. What was the problem? I think so. This started about 15 years ago. Well, started earlier, but so my experience with it. So in industry, so you had so did antibiotic research in particular when they have the possibility to sequence bacteria. I think this is only coming the last 20 years to could sequence it because before it was an enterprise for many people. And yeah, so then they launched. Yeah, thanks. So they launched the search for it, and so what they can do very well. So they make a high throughput campaign, and so they identify the targets, and then they want to make, okay, now we can solve the antibiotic problem, so we can make new drugs as much as we want. So imagine, so GSK, they made, for example, 67 high throughput campaign, and each high throughput campaign is something which is very expensive. So running many drugs and looking for whether they fit to the target, can block it. And then finally from the 67, only 16 they gave any hit, and only 6 were a little bit they could go further. And yeah, so and this was a complete failure. So as you could see it in this article from David Payne, so you reviewed it. What was so they quite this was not possible to go on. So, and the other companies like Pfizer, like Sanofi, also they had the same problem. So they started, they identified the targets. So, for example, there are about 180 targets in bacteria which are druggable, which are not in human. So this you can use to block and inhibit and then kill the bacteria, but nothing came out. So, and then so that means there's a low return on investment. And that means they stopped the research on it and they will not continue. So, and one of the causes was, it was also because when you look at the regulation for antibiotics, it's very complicated. For gram-negative, gram-positive, it's completely different, the regulation. It's a complicated structure, what you have to do. Despite that it's something lineage species by its own, you have to do this with human. So it's a little bit complicated. And so the industry abandoned this, although they had a lot of success, but they abandoned this because there was no drug on the market out of this. So And so this was the starting around 2010 when the people thought about, it's when nobody's producing antibiotics, what shall we do? So these are mainly gram-negative bacteria because they are problematic because they have two cell walls. So the molecule has to go from hydrophilic solution to hydrophobic, across a barrier to hydrophilic, and once again to hydrophobic. So this is difficult for a chemical molecule that changes pattern during that course. And so they have this, they identify the target. So again, to GlaxoSmithKline, they developed 10,000 compounds with nanomolar affinity to inhibit the target. So I think they have huge library of molecules, and none of them became a drug. So, okay, that was one thing. So, and the same thing, Pfizer had also the same thing, Johnson & Johnson, they have this drug, but it did not work when you apply it finally to the target. So one thing is about, they thought maybe it's because for gram-negative bacteria, it's because they have to go across the barrier for the membrane. So we should make a program to find a new parameter. So usually in the pharma, what they have the Lipinski rule of 5, so they identify the molecule what we have, so they put a pattern. This molecule we have, this molecule we have, this is inactive, this is inactive, and to look what kind of pattern this molecule have. So it's low molecular weight, below 500, 600. So that is a hint that you go through a channel because there's a size, because you rarely have an antibiotic which has a higher molecular weight than 500 or 600. So you have the number of hydrogen bonds, and you have also fairly soluble in water, and so on. And they thought maybe we could find out another rule to identify a molecule to make an antibiotic out of it. Okay, good. And so then they identified all of this. Nobody knew a little bit how to transport across the porine of this membrane channel outside. So that maybe is the question. We should understand it, how a molecule goes through a channel. Good. And then European Union, sometimes they have really great ideas. And when they do in profit something, they have also have the money and have a budget. So what they did, there is this was independent from antibiotics, but there is an institution called IMI, Innovative Medicine Initiative. Is now called a little bit different, but it's still there, and it's now integrated in this research program. So they said there is an organization in Basel, which is from the pharmaceutical companies in Europe that are doing research, called EFPI. And so they sat together with them and said, what shall we do to enhance the research in Europe for pharmaceutical companies? We want to have more research in Europe, not only in the US. And then they said, okay, we cannot give it to one company, since that would be not legal, but we should have some. So then they came up with the idea, so we can make a larger project. It was a big project, which a single country doesn't make sense to run it on a single country. So European spirit, so several countries in Europe will contribute, and so we can share this. And it should not be only one company, it should be a different company. And then they said, at that time it was very popular, the company goes and comes back. We should go away from university, we should make a private-public partnership. So the university contributes something, the big companies contribute something, we put everything in the pot, and then we run a project, a little bit not like you do it, for example, for the DFG or RNR, you give money to someone, he did some research, he published some paper, and then, there's not, so they want to have it a little bit organized in a company type. And then they set up, okay, antibiotics, this is something which is actually run down, there is no hope for it. People left the field, and then they said, okay, we will make one big project. So European Union said, okay, we will, you raise money, and the industry should raise money, put in the pot, and we put money in the pot. So the European Union pay academia, pay small companies, and pharma is doing in-kind contribution they provide also a certain budget for it. So there was 1 billion from European Union, so this is 1,000 million, and EFPI 1 million. There's a budget of 2 billion euro. You can do some. 2 billion euro, you can do some, right? and they call it new drugs for bad bugs. And you know, and this is very modern. So whenever you have a pharmacology course or something like that, you have this scheme. So first you do early discovery, that is a little bit connected to university, then discovery, preclinical study, then the phase 1, clinical phase 2, phase 3, then they have the regulatory business, and then you have a phase 4, kind of to rule it out and make a they go to the patient. So they set up something like that, and the budget for this was 2 billion. Okay. And I'm a physicist, so interestingly, so somehow, yeah, okay. So so they are make a call, and then so we applied, and somehow, and so this is the project what I was the academic PI for this translocation. Or this was we should investigate penetration and how molecules go into gram-negative bacteria only. And then we have an info center that I will talk about this a little bit more. I think it's really kind of funny experience. Then we had Enable. This was run by people from Uppsala, and then compacted this clinical part. I think, of course, this were 30 million. This was about 60 billion, and this was the I talked about 2 billion, right? Okay. Clinics are a little bit more expensive, but yeah. So. Yeah, so kind of, I became the co-leader or the academic leader of this, and the main PI was Rob Stavanger from Philadelphia, from GSK. And so we wrote down this project. It was very efficient to write it. I think this grant, I think it was at the beginning, it was about 15 pages, and overall the contract finder, what we did was 300 pages. I think it was fairly easy to go. It was done. I submitted a DFG grant similar to RNR before, and I got the rejection after this project was through. And so it was kind of funny. It was very effective. I think I was deeply impressed. And so this was, we called it translocation. And so the content was getting drugs into gram-negative bacteria. So I did run from 2013 to 2018. I continued a little bit with follow-up projects, and then somehow, for the moment, I think there was another project is COVID, and then everybody from infectious disease moved to COVID, and kind of I was, you know, I can do everything, but I think I didn't feel so well. I was in a healthy state, but I think it didn't work. So the motivation was, you look at AZT or HIV. So HIV at the beginning of the disease, the drug AZT was really toxic. I think it was fairly toxic. Somebody who take it, you could see it from far away. So, and they doing this course of improving it, they could reduce the dose you need. And they thought about, okay, this might be something similar, because everybody knows when you take antibiotics, you take gram quantity, and you have problem with your stomach. I think whenever you take them, you have problem with your stomach. So it's not only that, and that is the least thing. I think you have other things, side effect. And so you take, because grams are less, no other drug you take in that amount. So they thought about, when we reduce, can you reduce the dose? We can optimize it. Maybe this could change the plan. So, okay, this was our project, how we made it. So it's interesting. So if you make it, what a pharma company can do when you have the target, they can find an inhibitor. I think this is a straightforward way to do it. I think it costs money, but they have methods to, when you have a target, they can find a molecule which blocks the target. I think so it's straightforward. I think they can be sure within a certain time they will get something out. So, but not for gram-negative bacteria. That did not work. So the selective inhibitor is easy. For the target you find, so GSK had 10,000 inhibitor. So when you see a publication that somebody found a new target and has found an inhibitor, and it goes to Nature, this is fine, but usually this is useless because such molecules are already at GSK, but they never published. So they know a little bit, they know these 180 targets, and I think they're very new mechanism which goes. So this, I think, be a little bit, yeah. So this is also I learned. Not everything what is in nature has also an impact on later on. So gram-negative bacteria, so I have to be careful with your eyes. This is the inner membrane, this is the outer membrane. The outer membrane has holes and a protein in which allows molecules to permeate. And so we talk about this. So this was our finding. So first, so basically there are few more bacteria which are the main important. Is Pseudomonas aeruginosa, Acinetobacter baumannii also recently. I think this was something. E. coli still is Klebsiella, and yeah, there's another one I forgot. So these are the main things which are troublemaking in the hospital. So, but it was not known what protein are there. So this was the beginning of this. So people did not know, that they could have the sequence, but they could not know what protein you had. So we should do we started with membrane proteomics to look what is there. And then we developed all cell penetration assays and cell-free assays to make the transport quantification. And then we did also X-ray structure. So I think in the project, I think also when I talk we, this means the project. I think in the peak time, we were 150 people. Not everybody full-time, but so I think it was quite a large project. And so we solved about, I think, 50 structure from Poland. So I think it was quite a nice thing that came out. And then we want to find out how what is the flux through a single channel. And then, of course, we were lucky or something that was nice because we had a lot of computer simulator, I think, which they provide us with beautiful picture and sometimes confusing results. But I think that everybody has it that problem. It's not only the simulation. And then the other one was hydrophore. For example, in France, it's Isabelle Child who did this also intensively. And novel uptake system, we looked at this efflux pump because the bacteria can also pump against the concentration and actively, of course, molecules out. And then the other one was, this is also when you're running a big project. So what often you get money to make a database. So you make a database, you get money, you put the data on, then the project ends, no funding, and the database goes to the archive, nobody take care. And so European Union, what they plan, also you might have heard it about verification. They want to have, when you have a project, what are you doing with the data? So if you put a database, you get money to make a database, but not for maintaining it. And so they came up during this process when we worked on this info center, and this is something what continued later on with other projects. It's called verification. So we should make the data what you have, you should make it in a process that you can retrieve it, and you have also put it in a manner that you can use it for other things. So like you have a computer program that you can also use it, the data itself, you can use it in a format which is usable. And so this will maintain in other EU projects, you have to put it in a format and have to try to upload in a way that is maintained and people can use it. I think there are many databases nowadays, but so they try to unify it in that way. Okay, so next. Yeah, outer membrane proteomics. So it's maybe, I think we were lucky. This is a colleague from the Biocenter in Basel. I think this was someone who fairly innovative, hardworking, and I think in the Biocenter in Basel, I know this personally, money is a problem. I think it's simply there, so you have to convince people by innovation. So what he did is something a little bit crazy because Pseudomonas aeruginosa, so this is one of the troublemaker. So this is a sketch from Hancock's review. This inner membrane, the outer membrane, these are some of the protein. You have all type of channels inside this for particular harvesting and selectively uptake molecules, amino acid, glycose, antibiotics, and so on. So, and he did proteomics, so he was able to identify what kind of proteins you have in the outer cell wall. Also, the inner cell wall, he continued that. And then, so he found, for example, there are 60. It's not only this 1, 2, 3, there are more than 60. And then you have also uptake system actively with ton-weight event, so you have more than 35. I think you have found even more. But it's some kind of this bacteria has funny composition, so they have all kinds of things to survive. Also, Pseudomonas aeruginosa, they can live on soil, they can live on here, they can live there, they're everywhere, and of course they are there. So what he did, so he quantified how many copies you have. And this is Julien Beuk. He is now, I think, in Poitiers. This guy was really tremendous. I think he did all kinds of identification of this, and he did also a knockout mutation over several years repeatedly. Of course, he had a Swiss salary, but I think it's frustrating when you make all one more, every week you find another protein which might be important. And then so he's really hardworking. I can recommend him. And also nice guys. So, and then what he did, so he tried to make proteomics and quantify this. So this is a cartoon. So you have 10 to 5, so 100,000 copies, 10,000 copies in this range, or 100 copies, so they could identify what they have. And then you look at whether you have the infection in the lung, in the blood, somewhere here, somewhere here, and in different artificial, like Müller-Hinton broth, or what kind of media you let them grow, and you look what kind of things you have. And so you see that sometimes OPRF, this is always there, and then you look at this, and then you keep on going, and so he did many different conditions to look at that to give a number, because nobody did that. And then of course you have also at the end he did also clinical studies, so he got also directly from the patient. The point is that you cannot grow them, because when you grow them from the patient, you put them in your cell culture and grow them, it's different. That changed with the next generation, that changed the composition. So you can't. So it's quite a little bit tricky. He did a lot of work, I think, and I think it's also finally he published it. I think this. So you see this was published at 21. So it's 3 years after the project ended, and he worked for 4 years on it. I think so. It was really a tremendous thing. Also a lot of discussion, and but you know, the data is there. So okay, so it's more complex. So whole cell assay. So I think it's a little bit tricky to measure it. So the bacteria are very small. I think this is nice sometimes, but you can't. On a single bacteria, there's nothing in. And then, in particular, gram-negative bacteria, they have this periplasmic space, which is a very thin layer. And so, okay, in order to quantify it, you need my light. Yeah. So what they do, you put the drug in E. coli, put it at 37, let them grow, shake them, and then it comes a little bit of an art business, because you have to separate, you have to crash the cell, and you have to separate what is out and what is in. But that's fairly tricky. I think there's 3 or 4 groups worldwide doing it now, and it's very tricky, and you have to be patient and have to be sure that what you are doing, I think. And then, okay, for the analysis, I think it's, radioactivity, I think is not a good idea, because for high throughput screening, you would have to label 1 million compound. That's not doable simply. I think so. It's they don't use it. Fluorescence, you need a molecule which is fluorescent, and or mass spec. I think then you have to do also you have the separation. So because you need the cell count, so you can amplify. This is easy. You can get a liter, or you can get a kilogram if you want, but you have to separate the outside from the inside. So that is a tricky part, which is an art itself. Okay. That is so there's mass spec. I think it is nowadays that what is really doable. So and the development for the chemist, I think in mass spectroscopy for the sensitivity, I think it is really. I think I have seen the old mass spec where this machine filled 1 room, and I have seen the latest thing from a book that you can take home. I think you can carry it, and it's incredible. Yeah, okay. Then optical measurement, but you need. You need fluorescence. You need something to see it. You need, for example, what we did also with artificial amino acid with fluorescent band to get it on the fly to measure that. That's also a little bit tricky to do it, I think. So this is, for example, from Jean-Marie Pagescu and the beamline here in Paris. So you see the bacteria. Okay, here. It's a little blob, and then you identify how the fluorescence, you have the antibiotic outside, and it will accumulate inside, so there's YIP, and then it will take a while, and then it goes in YIP. So it takes about 10-15 minutes, and then you can analyze what is inside. We did with Uli Kaiser, we did also something, and then Uli Kaiser had a microfluid, and he wanted to do the antibiotic. So you get our porins, so you have a pure membrane, and you put the porins in. With giant liposome, you can use a microscope, and you can count the fluorescence inside. Liposome membrane, lipid membrane are not a good model for antibiotic uptake, because the bacteria out the cell wall is completely different. It's much more rigid, it's substantially less permeable. I think you can't really compare that. Also, you have to put porins inside, you have to fill it. And imagine this small bacteria, which is 1 micrometer wide, has a few 100,000 proteins. So and it's tight. And so it's not, so we got some numbers, but okay, I'm not so, it's maybe not the best one. Then before we started, so AstraZeneca in Waltham, so they looked in the literature, they looked at clinical strains and looked at substrate, which can be taken, but they looked at the literature, what is taken up, and they identified the porins and the substrate. I think that was a hypothesis because it's not a clear proof of it. Because, of course, yeah, what you do in the biology, you make knockout mutation, but that is, for Pseudomonas, that's a failure. Julien did knockout mutation. He knocked out 60 porins. Yeah, okay. No. And yeah, so we looked at, he didn't find anything. So if you have 60 knockout mutation and no phenotype, yeah, I think it's okay. So this is my favorite picture, which I've taken from Kleine Kartoffel. So it's nice to have computer modeling because you get this colorful picture. I think this is what you want to see. Of course, we don't have this microscope. I think we have something else with a porin, and then you see it with a modeling. And of course, at this level, I think I think the molecule doesn't have the size of this level. So I think it's so this is the whole, and then so that is what the people like to see. That is an antibiotic, ampicillin, which is snuggling through, and then so yeah, we had two great crystallographer. So Jim Naismith, he was in St. Andrews, now he's in Oxford, and Bert Vandenberg. I think both are really great guys. I think they really did a lot of structural work and also very open and putting things forward. I think it's very impressive. And yeah, so I think that they found the crystal structure from Klebsiella, Eosinus, Slovakia, and so they found many. We did uptake measurements, and then we looked at what is the difference between them and try to conclude something. Good. Not only these are also some tiny from Acinetobacter baumannii. This was not so interesting before, but now it becomes interesting because of the resistance. So this is one that is KO. This is a funny thing. So it looks, very controversial because you can go to computer modeling, you get different results depending on the computer model you go, which is a little bit dangerous. So then it's not so clear what is the function of it, but basically it's likely like A or OPIF, it's a structural protein because it's very abundant. So basically it maintains that the structure of the Pseudomonas aeruginosa. Although this is the only one which is supposed to allow antibiotic go through. But yeah, okay, we don't know. Then we have others who we investigated also transporters for many of them. So we have a number of porins which are interesting. So the point is to measure how many molecules going through one single channel. It's a little bit tricky because the distance is 4 nanometer. So you have to measure how a molecule diffuses 4 nanometer. If it's free diffusion, it takes nanoseconds. And okay, so you need some tricks to get it. So I think what are the rules? How to bring a molecule through hydrostatic pressure? I think it's not possible. I think if you want to put with this small Hagen-Poiseuille, if you want to put, they have 4 nanometer length, you have 1 nanometer in diameter, and want to put a flow, I think you can't. You need a 10, 15 meters water flow. This is not a relevant thing. Membrane potential, of course, when you apply membrane potential, but across the outer cell wall, there's not much membrane potential to put something neutron inside on. But this for us what we can do, because in the solid state we can crank, we can go to 100 millivolts, 200 millivolts, we can go to, in the solid state we can go to 500 millivolts, we can go to 1 volt, and the instrument break because of the substance to burn, but not the pore. Okay, and then of course at this level diffusion is the most important part of the concentration. And then the other one, which came over the years, became more and more important. I think everybody has now papers on it. So convection, this is electroosmotic flow, because you have the counter ion sitting there. You apply a voltage to attract the counter ion, this creates a water flow, and that brings other molecules in. That is very interesting for us because it's as a tool from outside. So yeah, okay. So that's what we want to study. What is kinetics? What is the origin? How we can trick it? So free diffusion technology. So we need optical signals or electrophysiology or something like that. So what we do, I think it's also in Cergy. I think it's something our goal. So you have a current, and then you get dimples. And then you get a smaller one, we do not know what that is, and get impulse. Then you change the condition, you get less. Okay, and then you need a little bit of model. And then you can say this is that, this is that. Yeah, then you have to be sure that your model has anything to do with that what you measure, and that what you measure has anything to do with reality or with nature or with making a new drug. So I think these are different steps. I will not go into the equations and in all the details. So we have many of this, and we published a few things, I think. So computer modeling, I think so. This is the crystallographer, Bert and Jim. And this is Matteo Ceccarelli from Cagliari. And Uli Kleine-Kattel, he's German, you see it, and the other one Italian. It's interesting, both use a different computer program. And yeah, I think I could also show this computer program, but I didn't link it. So you could see how a molecule, ciprofloxacin, is snuggling through, and you can identify the side chain and the point, and you get some ideas. Beautiful. Yeah, okay, good. One thing is, I found, although this is old, I think, OMP-F, so there's a constriction. So this is a trimer. So this is we look on top of this trimer, and this is apparently the hole. The question, what is a hole at the molecular level when there is a nanometer difference? This is not the real sharp edge billiard ball type hole. So on one side you have positively charged residues, and other negative. So there's in the middle, in the constriction, though, there's something which makes it very small. So there's an access funnel and an exit funnel in the middle. There's a huge dipole. So this is negative, positive, this negative. Between here and here, it's only 1 nanometer distance. So this is something quite strong when you have a polar molecule, because it will orient that. If you have a dipole, it will act on that. And most of the antibiotics, what's going through, they have a size, they have a length, and they have a dipole. And this dipole has to match that the molecule can go through. Otherwise, it will not go through this. And many of these channels have a similar type of selectant, but this dipole is the selectant. And so what you can also do, then you can average where the molecule going. And in OMP-F, it's a funny thing. So the cation going on one side and the anion going on the other side. So because of the affinity of the molecule to one side, you get a movement along the surface dominantly. So the molecule mainly move along the surface, they glide along, and they are not away. So you could, this is one of the way how you nature select molecules that have an affinity side where the molecule going along, I think. So that is my interpretation. I think this, but they are beautiful picture, I think. This was the first one, my student, Christophe Danilor in Toulouse. He did some hand waving simulation, and he put basically the structure. I did it for 20 years ago, I think. Even in Blanca, I think this was his achievement. He put an ampersand molecule by hand in. And I think this was quite, I think it has nothing to do with it. Yeah, but doing more sophisticated one, you come to a similar conclusion, but I think this is, you can do this with hand waving. So the problem is also was with modeling was you have a poor statistic and you need kind of a force to put it through, and then the averaging. But maybe nowadays, I think that artificial intelligence and ChatGPT, you can ask them many more questions. Yeah, so that's what we get out for your avibactam, for example. That this is along the energy barrier along an OMP-F. So let's see it fades away. Okay, no, it's okay. But you see, it's a little bit cation selective. So the energy barrier for negative for the chloride in the middle is high. So they hadn't overcome a barrier. Where for it's cation selective slightly, so you have a little bit of dimple. So you have get an affinity of that. Whereas the antibiotic avibactam, they sit somewhere, they have a binding site. You accumulate them, and then they jump over the barrier. So I think that's the only part that we get. Yeah, we did it for many, I think. And yeah, okay, this Monday, I think. Yeah.
Energy barrier just for anion or cation?
These are several. So of course, this nice thing at the computer modeler, you can take one atom and you follow it, and you forget about the other, and then you get a statistic, because in electrophysiology you make always the current, so it's plus and minus together. You can't distinguish that. So and they can do it. So this is for chloride. So it comes from one side, and there is a barrier in the middle, and for the exit. So this is a very shallow barrier, but it's something about 2 kT on a kilocal per mole. I have to convert. For the potassium, it's a cation selective channel. So they have a little bit of an affinity, but still there is some barrier, but there is an affinity in the middle. So it can go easily, much easier through than the chloride. There's not much difference, but this is a substantial difference. It's a noticeable difference. Whereas for these are small inhibitor, efflux pump inhibitor, so they accumulate, because these are not general molecules, but these are proven molecules which are effective. So they go in, and so they have an affinity site. So they bind here, they come here, accumulate, and then once in a while they appear, and once in a while they're going out there. The same thing, a little bit symmetric. So you have an affinity. So good antibiotic often have an affinity next to the barrier. And then they have a high chance, because they have high concentration, there's a high chance to go across the barrier. So this is somehow how laser go to something which they should not go. Of course, it was not optimized in nature, but I think other molecules have been optimized to do the job. So I think this is how you find the
competitive the affinity between
yeah, no, okay.
The question is, I don't know if you consider the difference between
okay. I see your point. And the computer modeling of top, they take the trace, but they have both. It's selectively neutral, but they follow one trace, but they have also the counter ion. I will come in the next slide. I will tell you what is the problem. And that you're perfectly right. I think there is a problem, because when you go in the books and the textbooks and the electrophysiology, and then you go for Nernst-Planck equation and so on, and then you look, because like in pharmacy, you take the backside. There are some warnings. I think how do you say, trigger warning or something like that. Be careful. So when you use always this simplified model, like with Chapman, for some Boltzmann, everything which goes, they treat. There is no interaction among the ions. Oh, come on, they're close distance. There is an interaction here. It's neglected. So all this model, simplified model, Boltzmann, Hodgkin, Katz, and so on, all they're using the assumption that they don't interact. This model is more sophisticated because they use the presence of that. But what they used is not very good for water. It's a simplified water model, and so what we did, I think because the good thing when you have two colleagues which are a little bit in competition, not too much, I think, but sometimes it's annoying when there are too much competition, but because then you find out also, because when you use two different models, they should come to the same conclusion when it's relevant for the order to find out why it is neglected. And one thing is, so what we did, we tried to do measurement at high different temperature and look how that behaves. And this is something what the computer model can do easily, because they can switch the temperature and can run again. It's not much work for them. Of course, they use the computer all day, so I think, but it takes them a short time then to get it. And then we look at the temperature dependence and look at things like that, and then we try whether we get the same slope from the temperature dependence, because the absolute value sometimes are a little bit off to say, yeah, but okay, there's a factor of 2, we do not know, but it's something you multiply everything with factor 2 is fine. But when you look at interaction, then you make a different temperature, the same reaction, and you measure it, and then from the slope, this tells you about the enthalpy contribution. And if you don't get that right, then there's something with your energy potential wrong. I think so. This is somehow what you can do. So this is what we did with the several things. So you're right. Okay, good. Next slide. So this is what we did. I think basically we went back to the Goldman-Hodgkin-Katz equation. How to get a number out of the flux, because it's cation anion you cannot distinguish, because they do not know what is a high and low flux. So there are a little bit tricks, because you can go for when the cation and the anion have a different speed, you create a potential. This potential you can measure, but you need two charged molecules. then both charged molecules have the same velocity, the electrophoretic movement is the same. You can't distinguish them. You cannot say whether you get a current, but the cation is going there, the anion going there. There cannot be two cations going there. And so the way how we measure it, because you have the electrodes, so it's an open system. So it's not something which you get in equilibrium. But, so you have to see it, but so you can do some approximative approach, accounting that ions don't interact. There's no interaction with the cell wall. That is okay. Point like particle, I think, which is not fulfilled. And then you make a table. I think so. This is funny. I think this is good. So this has been done under that. So we measure numbers. I think we take a protein, for example, OCD1. I think this is one of this. Okay. So and we measure. We make our electrophysiology measurement, and we measure how many. So we put 1 millimolar concentration there because we have to go for high concentration. Unfortunately, not really realistic because normally you have less for antibiotics. But otherwise, we cannot. Our electrodes are not sensitive in less. So when we take sodium glutamate, so the sodium and glutamate, the sodium there are 5,700 per second per channel. Okay. And the anion is 1,800. Good. And then we go, for example, lysine chloride. The cation lysine is for 2007, 7,300. Okay. Now we take histidine chloride. So the chloride is the same. It's an order of magnitude. So the assumption how we get this number are wrong. So we have this model of how to calculate it. So the ions are strongly interacting with each other. So everything which based on the non-interactive ion is wrong. Okay, now you can say by principle everything is wrong, but it gives you a number, gives you some trend, and it gives you some warning when this, otherwise you don't get a hand on it. And so you can see the chloride here for this channel. So it is 626. So I think the ion knows what kind of counter ion you're using, but for pharma, it is not so interesting because you need sodium as a counter ion, chloride as a counter ion, or proton. So you don't have so many counter ions in the drug. So you cannot, otherwise you could do something exotic thing, and then you could play on this thing. But it's interesting. So,
and in the net flux, you have to consider also maybe the relationship.
Mm-hmm. I think, but but it's something. So it's not something to compare so easily because it's a counter ion method, the interaction with the surface method, and it has a big effect. So I think it's so to understand the general problem. Of course, I think it's with this method we cannot go much further. So I think I think it gives you a number, but a clear station can be an order of magnitude away. I think, and this is something you have to live with. It is like that. So I think you have to go for better techniques. So you have to understand that this is a correlated system. It's not an uncorrelated system. So okay, good. Okay. So and then I think from Newton molecules, hey, you can't use it. Good. So then we said, okay, we played around. So what we want to do, this is a little bit for you. I think just like so, yeah. So I think we got electroosmotic flow. I think it came out. I think Hagen Bailey put it somewhere, and then somebody when Hagen Bailey does something, everybody repeats it. And also finally, also a few years later, I understood it. Also, this is interesting, so I did it also. So okay, good. My student did, but now I can say I did it because now I'm doing the measurement. Yes. Yeah, good. Okay. So this is a foreign. So the electroosmotic flow. Let's say this goes in this direction. Okay. Then you add an uncharged molecule, and this goes with the flow, and it goes in, blocks the channel, and then it goes out. Boom. Okay. Then you have two things. You increase the voltage. You have case one. If you increase the external voltage, so then the electroosmotic flow will be stronger. Then you have two possibilities. Either it goes faster, this means faster, or less. And then, or it gets shorter, so depending. So you can conclude when you increase the voltage, increase of electroosmotic flow, if it cannot go through, then it has to go exit by here, otherwise you will not leave off. And or you can get the ratio, I think, and play around a little bit. So simply looking at the dwell time, resonance time inside, and as a function of external voltage, you can get some information. There is a way how you get a number out of it. I think it's not something very precise, but it is a way how you can measure something which you can't measure by electrical field, by current measurement, because it's neutron. Okay, so yeah, I think so everybody knows it. But it was also something funny because we discovered things which has been done 15 years ago. I think so it's always speed up. Bacteria are a little bit funny because you cannot take off both membrane proteins. There's no way once it's in, it's in. But the bacteria, what they do, they have a way of the system to talk with each other. Now it's exothermic and exovesical, because it becomes now fashionable, because bacteria can bud off part of their membrane. It's supposed to be a copy of the membrane to eject them and secrete them. And we could put them in, fuse them with lipid membrane. And then you could measure a little bit to get access to the LPS membrane. That is also a barrier. I think it's a funny thing. I don't know why it works, but then you have to go back, or you have to read carefully the biological paper, which is saying that these extracellular vesicles are heterogeneous. Heterogeneous, they're not homogeneous, which means you select for some, but not for all. And so some might be fusogenic, others might not be fusogenic. So, okay, good, okay. Then, sometimes you're getting brave and then you have good friends. So I have a good friend, Jean-Marie Pagès in Marseille. And he said, also, you should, Mathias, you have to do measurements, you have to do this, you have to do that. So he so he measured the intercellular concentration by mass spec as a function of time. So he had OMC, this is one, he revealed it after 5 minutes, 10 minutes, 50 minutes, and he measured by mass spec. Of course, this is an average over many of a cell culture, and you get more. So you get more. You get more and more. So it goes at the beginning, well, you can say it is linear, and then somehow it's a plateau. I do this for another one. It goes also up and down. And so he gives me a number because he has a number of molecules which accept acetylene, which went in, and he can estimate how many bacteria he had, and then he can get a number. And then, brave as we are, we do our by electrical measurement. We take the protein, we put them in and measure how many molecules. And I think it's funny when you work with a colleague. I think they look, must get about 300 molecules per cell per second, and single channel get 400 molecules per second. Yeah, the only thing that the bacteria has 50,000 protein, which means we are off by 50,000. I think I can divide by 50,000, so I think it's not that problem. I think mathematics is still a little bit, but so there is a problem. So you can always say that ignore everything, but then because I didn't want to throw away my data and I want to publish with him, and so there's one explanation, because the periplasmic space is very crowded. So when one molecule goes in, it's already high concentration. So from the gradient, I think it will go out and the next one come in. So it's not, you cannot really accumulate. And so this is something what we have found out also doing several, we did a few other studies. So when you look at it, for example, what you can do, you make this hybrid molecule, and I think, can become, you need, for example, this maltose binding protein is also something that means, so you have a few, what the people like now to make hybrid molecules. You have an antibiotic, and you put a molecule, they find their way in. So, for example, you take a maltose, a multi-oligosaccharide, and put an antibiotic, or you put a fatty acid, you put an antibiotic to fatty acid, or you have different ways how you can put it. And surprisingly, when, for example, you take a cytophore, which are ejected because the bacteria need iron, and you put on the other side of the you have the catechol, and the other side you put an antibiotic. So by buying the iron, it will be taken up, and then you have an antibiotic inside. So this is a kind of a funny thing, because this hybrid, this boy and horse approach. And the thing is that this is a way to accumulate antibiotic inside the periplasmic space. And we did this, Jean-Marie. So, we didn't do it with antibiotic, we put a fluorophore in, so we could measure the fluorescence. And indeed, it goes fairly well in. I think this is something which is a sugar which goes in, and then you have another antibiotic, and it goes almost as good as. So you can use this as the rocket, and this is basically the cargo. So this somehow the wall, or how you say it. Okay, so this is one thing what the people do, and it might be a solution to make this hybrid molecule. A number of solutions. Yeah, and then I want to close this part of the chapter. So, so the project ended in 2018. Well, there was some intermediate step where there was, when you run this big project, there's kind of a, yeah, I was on the table on this very big project where the people shared money and information about, this clinical things. So it was kind of funny. I think I knew it was an experience for me. And so the point was, at one point, AstraZeneca dropped out of the project in the middle of the pathway. They stopped it. All antibiotic research closed. Said no, this is no interest for us. And then at the end of this project, there were apparently another 20 billion hanging around, but finally there were other people who were more greedy. The money was away, so there was not a co-investment from the pharmaceutical companies to get a prolongation of the project. They stopped. The pharmaceutical company all pulled back. So Glaxo continued a little bit, but they stopped it also now. Sanofi stopped it. They sold to Evotec the project. So the antibiotic, they moved to Lion, and then they gave up the antibiotic research, and they sold it to Evotec, and Evotec received from Sanofi 60 million to take over this part. I think that's a little bit weird. You sell your company and give money, they take it. So because they simply said there's no others should continue, so they don't have to lay off. So they didn't see any future for them. Although they have the molecule, but no way to put this molecule, what they have, to put them into a drug. I think so. This they moved out, and and then the European Union and also US, they put a big project on it with a certain delay, and they put a big project to sponsor smaller companies to make an investment in antibiotic research. That took over, and then the European Union, and together with US, because originally this project was supposed to go in collaboration with US, but US, because of the election of the previous president, they could not, the NIH did not get the funding, so they didn't continue, so there was a delay. And then the US took over. There was on several funding, like also in Denmark, there's a big company that gave a lot of money for creating a startup company. So there's actually a reflection whether we should not give money to someone to develop an antibiotic, but sit there like a poker and say, when you have an antibiotic, we can buy it. The so-called pull incentive. But the question is, who is paying for it? Because if France will sponsor antibiotic research, everybody else will be happy and will buy them for cheap. Or what is a new antibiotic? Because when you make a side chain modification, this is not much money. Or is it has to be a new class? What is a new class? So, and who pays for it? So this is still a pure open thing. Now there are more smaller new companies that try to invest in antibiotic research. But because during COVID, everything has been a little bit turned around, because infectious disease went basically for COVID research or for viral research. Now they're coming back because antibiotic, we need new antibiotics, but this is a remaining problem. So, but I do not know exactly the latest stage. Okay, so then what I should do here, I think I've heard is collaboration. By the way, these are the people. I think, I did not like those people that come at the end of the talk. They come and say, these are my co-workers, and they have about 150 co-workers. So these are one of the meetings what we had in Bremen, and I think the peak time we had 150. I think, but these were independent teams. We have simply to guide them. We could also shift the budget. This was not very much like for those who have to give it up, and it was an interesting affair. So this was GSK, Basilea. This is basically Roche, former AstraZeneca, Johnson & Johnson, Sanofi, and then you have a lot of small companies and universities. Okay, good. Yeah, collaboration. So I think I know already Ulrika from long time, so I want to make a collaboration or continue beyond the weight collaboration of its meat and the retin. So these are kind of cysteine mutations because we want to put in the protein, we want to put particular molecule or cages or so to reduce the size or to make it more sensitive. Because as we know, we need an affinity inside to sense for molecule or to see whether the molecules are there. And so we have created a number of the good thing about this protein on PEP, we have only one cysteine, or they have no cysteines, but they have one when you introduce one. So we mutated at one point, the exit, we mutated this, and then we put a cysteine there, and then we put small chemical labels or a glutathione on there and to reduce it more. And this we got already, you see the difference. So this is arginine. When you put the wild type, you see nothing. You can't discriminate it. When you put the small labels, you see with glutathione, you see more spikes. For triarginine, you see something here, you see a little bit more here. And for heptaarginine, you see a change in the pattern. So I think that is something what you want to go for in the next step. So this is somehow what we like to do. And yeah, so the current thing, what I'm doing is going for a sensing, so I have everybody does. So this is a picture from the task group. So they used our OMPEP, and I think OMPEP has in the middle very strong this dipole, cation anion, cation here, anion here, and then the counter ion, they move depending on the field. So for positive charged analytes, you can put electric field negative, so you suck them in, and the electrosmotic flow is also going along because the cations are negative one. Okay, the electrosmotic flow goes in this way, and the electric because of negative one, it will go up. And for neutral one, there's only the electrosmotic flow. And because of the strong dipole, what you could see because of charge molecule, aspartate, when you have a D and L, it will bind in a different manner. The structure is different. So it will inhibit the constriction zone in a different manner, and you could see a clear difference in signal. So that is something, it's general what you can do. Okay. Then, as I moved from the biolab or from a biophysical lab to solid state physics to Hamburg, so I thought I have to work on a hybrid material. So the guys in Hamburg, they can do all kind of nano patterning of solid state, molybdenum disulfide, graphene, or whatever. So there is in a few articles in the literature. Of course, Stephen Bailey did it. So in case picker. So you have an hemolysing, you put the DNA, and you put the DNA in, and the sort of DNA, bomb, and then it's some partial close, and then you would have this permanently inside a solid state nanopore. Yeah, there's another paper from in Canada. Gupta, I think they did also a few of them. You take molybdenum disulfide, this is a thinner material. They drilled a hole with them inside and put also an OMG molecule. This is not so considered as being good because it's very noisy by itself. So on that I said, okay, we tried that, and we did also ion-focused ion beam, but our tool in Hamburg was only 18 nanometer. I think that's not too long. So we had to improve it a little bit. And then, of course, I know Benjamin with his top secret, but many Manu does. And he has also some toys. And then last year I came by and we got some first result promising. And now I came here for a longer period. And now we're going to do something real, means publishable. So why Cergy? Because I think, yeah, okay, they're nice people. I think I have been not the first time here. I've been quite often. I think you know also many years. I think. And Rania, they have also, you have been since a while, I would say. So I've been there several times. So they have a nice instrument, a nice lab. So this is basically the preamplifier and the Faraday cage and the nice cage. So this is the amplifier. I think this type of measurement, they are fairly easy to do and cheap because you don't need something like a million to start with. I think a single molecule. It's cheap. Yeah, no, but I think it's
cheap for French people, no?
Yeah, no, yeah, but I think it's something when you want to do single molecule detection. I think quite often you need a million upfront to see anything. I think, and then you, yeah. yeah, you see that I'm not too clear because there's something going on. It should be.
Why are you here? Because I don't.
Yeah, but and then of course, why Cergy? Because I think Cergy point was well known for digging holes. Yeah. But, you know, I found this, but yeah, so I think they know how to make holes. I think this is something that, you know, this is a simple instrument, and this is like a holder. And but these are a little bit the you can make easily for 2 to 10 nanometer. You can easily or control level. Not every day, I have to say. Also, you can make holes about it. Good. Okay, so far so good. This is a very short conclusion. I think it's. I think so. As you said, permeability is not one parameter. I think permeability, you have to say what is the molecule. If it permeates, you have to say what is the solution, what is the boundary, or how this the mechanism. I think so. This is permeability depends on many parameters, and I think it's a fundamental parameter for life, also for detecting our systems. So I think it's to understand it. I think it's quite useful. So I like to sell my proteins because it's a trimer, and it's unlike hemolysin or so, aerolysin. I think it's basically a trimer, but 3 independent, and it's basically one polypeptide chain. So you can make easily mutation on one particular position. You don't have to bundle around so much. So it's maybe more easy. And also OMF is something very robust, but I think that is also hemolysin is robust also. And I think it's quantitative measurements. I think always when you want to get a number out of it, it's not so easy. And then you get a number, then you have to verify this number, but this has something. This is close to reality or what that meaning. Because we get, I think, since about almost 20 years, we sell numbers for permeation, but I think quite often we found out this is not permeation, it's bouncing back. And I think you have to be very critical when you get at this level a number and how to compare it to other. And so the selection filter or the discrimination, I think so it's quite the size, but it's not only the size, it's the charge, dipoles, and I think so. And of course, I think it's biomarker detection. I think this is a big field, and I think so. We can do a lot of it, and I hope that I can continue. And so I enjoyed the life here, and although the weather could be a little bit warmer at this time, but I think it's I'm used to that in Hamburg. So, and thank you very much for